Hi, everyone. Thank you for joining the seminar. Our next speaker is Agata Lonc. She is a MSc student from University of Warsaw, which is in Poland. So we have an international speaker today. And her topic today is mathematical modeling of bacteria spreading in the interhospital network. Agata, you can start.
Okay, so my name is Agata Lonc, and today I would like to talk about the modeling of bacteria spreading in the interhospital network. But I would like to focus on the modeling of multi-drug resistant bacteria. This is a very serious threat in the modern healthcare. Even though now we are mostly concerned about COVID-19, there is a vaccine for COVID-19, and we have no medicine yet for the multi-drug resistant bacteria. And the usual prevention strategies fail in this case. So from the data, we may see that most of the transmissions happen inside the hospitals. That's why, in order to model the transmission and in order to maybe test some new prevention strategies before we implement them, we need some. So we need data describing patient movements between the hospitals. Unfortunately, such data is not available. What we do have is a data set, actually a few of them, provided by the health insurance companies. And these data sets contain hospitalization records, and in each record we have the anonymized patient ID, information about the patient such as their sex or year of birth, anonymized hospital ID, of course, date of admission, date of discharge, and diagnosis code. However, I should say that even though we have the diagnosis code, it usually has nothing to do with the fact whether the person is infected with the multi-drug resistant bacteria or not, because we usually don't conduct such tests on the large scale, and some patients don't know that they are infected because they don't have any symptoms. And by analyzing the data set, we also can later stratificate the patients, for example, according to the risk of getting infected. So first, I will present the idea behind the model of interhospital network and general the hospital network. And we divide the movement of patients into two parts. First part is the interhospital, so the transfers between different hospitals. And the second one is the transmission inside the hospital and the transmission of the bacteria inside the hospital. So if we want to have a network that will accurately represent the hospitals. And if we only had the nodes that correspond to hospitals, then as it is presented in the picture A, we would be only able to model the direct transfers between hospitals. However, there might be a case in which a patient that is already colonized by the bacteria doesn't know that they are colonized and gets discharged, and then later gets admitted to another hospital, and then they transmit the bacteria to another person. And in order to be able to account for such things, we introduce another type of nodes, the community nodes. And each time a patient is discharged from hospital, they go to the corresponding community node. And then from the community node, they may get admitted to the same hospital or the other hospitals. And there is no transfer of patients between different community nodes. And now that we have the network, we model the transfers of patients by Markov chain. And here, the figure presents an example of transfer matrix for this Markov chain. So we enumerate the nodes in such a way that first we have the nodes representing the hospitals, and then we have the nodes representing communities corresponding to the hospitals. And here in the picture, the color represents the non-zero values of the matrix. And in order to estimate the entries of the matrix, we consider average size of nodes, which we may get by measuring how much entries correspond to each hospital or each community in the data set. Then we sum how many transfers from one node to another there is each day in the data set, and we get the total transfer matrix T. Then D is the number of days in the data set. And if we have these three parameters, then the entry of the matrix is the entry from the total transfer matrix, so the total number of transfers from node I to node J, divided by the total number of days and the average size of the node. And then in order to have the stochastic matrix, the entries on the main diagonal is 1 minus the sum of the rest of the entries in given row, and we get the matrix with non-negative entries. And then inside the nodes, we model the transmission using a regular simple SIS model. For the hospital nodes, we have the standard notation. So S means the susceptible population in the hospital. I is the infected population in the hospital. Beta is the transmission rate, and gamma is the rate of removing bacteria from the organism.
We can't hear you, I think, or I can't hear.
Yeah, me neither.
Oh.
Something happened. Agata, I think we lost connection. So maybe you can pause the recording, Jana.
Okay.
Okay, can you see my screen again?
Yeah.
Okay. Okay, so then we can interpret beta over alpha plus gamma as well. 1 over alpha.
Start sharing again.
Your screen. You have to share the screen again.
Okay, I thought it was sharing already, but okay. Now can you see my screen?
Yes.
Okay, thank you. Okay, so 1 over alpha plus gamma may be interpreted as the time that in which as the time before an infected person in hospital is either discharged or gets healthy again. So beta over alpha plus gamma is maybe interpreted as the average number of new infections produced in a single hospitalization stay. And if we interpret it this way, then R0, so the basic reproduction number, is the sum of all new infections that that are caused by a single infected individual. So now I will present the model that shows the importance of transfers in the prevalence of the whole system. And we introduce a parameter tau, which is the transfer intensity rate. And tau equal to 1 corresponds to the situation in which we consider all the transfers in the data set, and tau equal to 0 corresponds to the situation in which there are no transfers between different hospitals. So once a patient is discharged, then they can only be readmitted to the same hospital. And then for any tau, we can define transfer matrix that is a convex combination of those two matrices. And here we have a few results from 3 different taus. So the top pictures represent the final prevalence in the system after the whole simulations, and the blue dots represent the facilities, and red the corresponding community nodes. The facilities are sorted by the parameter R0, which I discussed a few slides before. And the bottom pictures represent the prevalence on each day of the simulation. So each column of the matrix represents one facility, and each row represents 1 day of the simulation, starting from the top. And the hospitals are again sorted by the R0 population, R0 parameters. And we can see that as we increase the importance of the transfers, the hospitals that have low R0 have slightly higher prevalence. However, the hospitals that have very high R0 have much lower prevalence than they had in case of no transfers. So if we look at the difference in final prevalence between the situation for no transfers and full transfers, we get that for R0, it's for small R0, it's non-negative, but it's very close to 0. But if for the facilities with R0 greater than 1, then the difference is negative, and it can get very large. It may have very large absolute value. And so we can see that, surprisingly, even though we increase the transfer intensity, it does not result in increase of system level prevalence. And some could argue that this situation is even better because we have less facilities with very high prevalence. So what we can also do with the data set is distinguish patients into 2 groups based on the risk of the infection. And we can define high-risk patients based on their diagnosis. And in order to do so, we check all the hospitalizations connected with all the hospitalizations of one patient. And if at least one of the diagnoses is the same as as in the list here, then the patient is considered high risk for the whole data set. And if we define a high-risk patient that way, we see that total percentage of high-risk patients in the population is around 15.77%, and it's slightly higher among men than women. Furthermore, average number of hospital stays for high-risk patient is over twice as much as for the low-risk patient, and the average length of hospitalization stay in case of high-risk patients is over 2 days longer than in case of low-risk patients, and that means that it's reasonable to consider these 2 groups separately. In these pictures, we can see the differences in more detail. So we see that high-risk patients have much less hospitalizations of like very short hospitalizations. And similarly, on the right picture, we see that the total number of entries per patient in case of small numbers of entries is much higher for low-risk patients. And we can also look at the age structure, and there's no surprise that high-risk patients are usually much older than the low-risk patients. And what I would also like to present is how the percentage of high-risk patients changes in hospital. So in the left picture, we again see the matrix in which column represents each facility, and the row represents a day from the data set, and the color represents the daily percentage of high-risk patients. And the facilities are sorted by the mean value of daily high-risk percentage. And we can see that over half of the hospitals have the mean daily high-risk patients percentage around 40%. And the other thing that is important is that for most hospitals, the percentage stays more or less the same. There are some cases here in which we see switches between yellow and dark blue. However, this is mostly for very small facilities in which don't have any patients for some time, so the daily high-risk percentage is 0. And then they have one patient which is high risk, and it changes from 0 to 100%, but it's still only one patient. So here we can see in more detail that the values stay relatively the same. In the left picture, we see the differences between daily percentage of high-risk patients and the mean percentage. And in the right picture, we see a variance of daily high-risk percentage. And in general, the variance stays in order of 1/1000. And there are only a few facilities for which this is very high. But these are the facilities, this is the case of the small facilities in which one high-risk patient may change a lot. And since the variance is not that big in most cases, we can use mean daily percentage of high-risk patients as something to characterize the facilities. And the last thing I would like to talk about is the classification of the hospitals. First, I wanted to check if the parameters of the hospitals that we can get from the data are somehow correlated. We have 4 such parameters, and this is entries per year, patients per year, mean length of hospitalization stay, and the mean daily percentage of high-risk patients. Here it's written as mean DHR. And we see that the correlation is high only for patients per year and entries per year, and the regression line is not really important in the other cases. However, we can still classify the hospitals in some way, and to do so, I used the k-means clustering, and this is the algorithm that for a given number of clusters find such division of the set that for the sum of distances between each representative of a set and the mean value of the set is the smallest. And here we have the results for 4 clusters because that was the most informative from the cases that we computed. And here we see one unique group of hospitals, the group number 4, so the purple one. It is characterized by a long mean length of stay, lower than usual the mean daily percentage of high-risk patients, and small number of patients per year and entries per year. And the remaining groups have, on average, similar parameters, only they have different sizes, so the entries per year and patients per year. And by checking the hospitalization records, which are connected, which are happening in the hospitals, we can determine that the unique group is consists mostly of the mental hospitals. So the epidemic in mental hospital would probably look very much different than in other types of hospitals. And we can also see from the picture that among the remaining groups, the smallest hospital have the biggest variance of mean daily percentage of high-risk patient and mean length of stay. And it can be due to different factors. For example, it might be a result of smaller hospitals being less steady or having much more fluctuations in patients for some reason, or it can also be the result of incompleteness of the data, because in this data set we only have patients from one insurance provider, and as we know, in the hospitals there are usually patients from many different insurance providers, and we don't have a full picture of what happens in these hospitals. And these conclusions are used in another model, which describes the dynamics of patients of different risk groups in a single hospital. And that would be all for today. I've left some papers which describe this project in more detail. And thank you for your attention. That would be all.
Hi, thank you so much for your talk. So let me start recording.